Today I'm going to be discussing how to do questions 1 through 6 of the USNCO 2025 local exam. You can follow along with the exam and the solutions document in the description below. So question 1 is just testing some simple dimensional analysis. So we're given that we have 486 grams of N2O5 and we want to find the number of nitrogen atoms in that sample. And the first step is to calculate the molar mass of N2O5, which is the first line of this calculation here. Then from there, we convert our gram value into moles of N2O5, then moles of nitrogen, and then atoms of nitrogen to get our answer here. For question 2, this can be done fairly successfully and quickly with just guess and check and doing the calculation in your head. We're looking for a 1-to-1 mass ratio between sulfur and oxygen, and we know that sulfur has a molar mass of 32 grams per mole and oxygen has a molar mass of 16 grams per mole. So formally, we're essentially saying that the number of moles of sulfur times the molar mass of sulfur over the number of moles of oxygen times the molar mass of oxygen is 1. And rearranging, we get the mole ratio of sulfur to oxygen being 1 to 2, and that matches SO2 as the answer. As for question 3, the reaction that we're examining is 2Al plus 3Cl2 reacts to form 2AlCl3. And from there, we just do some dimensional analysis. And we have the gram value of 13.5 grams of aluminum. We convert that to moles of aluminum, then moles of Cl2, then moles of Cl, and then finally grams of Cl, and we get our solution here. This reaction can also be Al plus 3Cl reacts to form AlCl3, even though chlorine is diatomic, because it's the same ratios. So if you want to make your calculation a bit quicker or a bit simpler, then you can approach it that way and you'll still get the same answer. Now for question 4, since we're asked for concentration, we want to find the moles of iodide and then the liters of solution and divide the moles of iodide by the liters of solution. So we have two sources from which we're obtaining iodide, Ki and CaI2, and you can see the dimensional analysis here to figure out the moles of iodide that we get from each source. Then from there we can add it and we get 0.175 moles of iodide, and our volume of solution is just the 0.5 liters of Ki that we have plus the 0.25 liters of CaI2, which gives us 0.75 liters of the solution. And then finally we do the division and we get 0.233 as a molarity of iodide. Question 5 is a bit more complex in terms of the dimensional analysis and the stoichiometry, but to break it down, we essentially have an ore from which, and part of that ore is malachite, from which we're extracting metallic copper, and our goal is to convert our given value, the grams of copper, back into the mass of malachite, and then find its mass percentage in the 1 kilogram of ore that we originally have. So the mass of malachite, we're just going to do some stoichiometry to figure it out. We're going to convert to the moles of copper, then the moles of malachite, and then we have the molar mass of malachite, so we can convert to the grams of malachite, and then the percent value is just the grams of malachite that we have from the previous step divided by 1,000 times 100% to give us 8.18%. And question 6 is testing our colligative property skills. So colligative properties are properties of a solution that depend on the amount of solute that's being dissolved in a solvent. And it doesn't really matter what the solute is, it just matters the amount. And the equation for that is the change in boiling point is I, the Van 't Hoff factor, times Kb times m, where m is a molality and Kb is a constant for a solvent. So in this situation, Kb, since we're dissolving all the substances in water, the Kb is going to be the same. So we're essentially just looking to find the Im values and compare them and see which one has the greatest Im value, because that'll have the greatest change in the boiling point of the solution. So we can see this table here. The calculation for the molality, which is the number of moles over the kilograms of solvent, can be seen here, and we calculate it here. And as for the Van 't Hoff factors, these These three are fairly self-explanatory. They're ionic salts that dissolve fully. And then for sulfuric acid, though it is a strong acid, this only means that the first dissociation is strong. So it fully dissociates into H plus and HSO4 minus. However, it doesn't actually dissociate more from there that much because HSO4 minus is a weak acid. So we don't see it dissociate more into SO4 2 minus a lot. So we can estimate that the Van't Hoff factor is closer to 2 than it is to 3. So the IM value is close to 2.04. It's slightly more, but we can estimate it as 2.04. And in any case, we have the greatest IM value from Li2SO4 because it has a lower molar mass than Na2SO4, even though these two have the same Van't Hoff factor. So it ends up having a higher molality, and thus it has a higher IM value. And tying that back to our equation, that means a greater change in boiling point, and thus lithium sulfate, when 10 grams of it is dissolved in 100 grams of water, that solution will have the highest boiling point compared to the other substances.